Hey everyone, we are gonna go through another HEVD vulnerable driver video. So in this one, we're gonna cover use after free. It's a known technique. We're gonna cover many CVs as well with use after free technique on kernel exploitation. But let's first learn what is this. How to exploit this vulnerability. We will go through the source code thanks to HEVD vulnerable driver and the writers of this vulnerable driver, so that we can have a resource that we can learn the vulnerability. All right, so let's get started. As always, traditionally in the previous videos, if you watched already, I'm just giving a basic summary of what we exploited so far when it comes to kernel exploitation, and I'm not going to focus on the previous ones, but with this one, with use after free, we're going to exploit a stale pointer that's not freed, which is called through callback function to execute our shellcode after we can put into the memory there. What the hell did I just say? So we're gonna get into detail when I'm doing the source code review, and I will get back to this description saying that it's not just reading it, and we're gonna understand actually what did I just say. Okay, as always with the strategy, with the initial phase, I will go through the source code review. This is HEVD 2.0. You can also go through the latest version 3.0. I'm using 2.0 for all my videos. As always, there are two files, useafterfree.h and useafterfree.c. I'm also going to use the command.h header file to get the IOCTL code. I'm going to show you guys a very quick way to calculate the IOCTL code using the command.h header, but we can also use IDA however you prefer. This is just very quicker way to handle it. Windows is just working in the background. Anyway, for our strategy, we're going to go through the source code review first. For this one, we're going to have 4 different functions in the C code. So it's going to take a while for us to understand. We're going to see if Windows API calls that we need to learn. I fired them up in the background. We're going to go through these as well to see which parameters each function take. We're going to find the IOCTLs. You will see how quick we will do it. We're using Python. And then we will verify the vulnerability with each script, and we will go through our strategy to exploit use after free. And it's a pretty funny one. I think this is one of my favorite exploit technique when it comes to kernel exploit that I learned so far. It's kind of complex in the beginning, but it gets easier when you follow it up. Cool. Let's start with the source code review. If you look at the header file, there are some variables or structures defined in here. So let's see what are these functions are in the C code. So if we go through the comment section, we will see again some of the structure variables defined, and the first function that we have is allocate UFA object. So I also went through, I also go through my notes in here, one note. I will just publish these in a bit while I'm editing this video in my blog post. So it should be available while you're watching this video, and you can just go to ru103.it to check these notes. This is on my local at the moment. So let's see what this function does. Allocate UFA object. You can also check my notes here, but I will make it a bit bigger for you to see much easier. Okay, let's see what this function does. So first of all, as you can see, the author already commented all of these out. So even if you don't know what this function does, this is the perfect way to learn all of these. This is a great learning resource. So first of all, this line that you're seeing in here is allocating a pool chunk. We are using non-paged pools in here. We're going to get into more details in the next videos when we're learning about pool overflows. So if we go to this function x allocate pool with tag, let's see which variables does it take. First of all, it's a pointer void. If you look at this p use after free, it's obviously a pointer to use after free variable, and it's defined in the header file in here. Where is it? Here we go. So this is a pointer to the p use after free is a pointer to the use after free variable. Cool. So we defined it in here as it's explained, and then we have the pool type and the type given in here, which is non-paged pool, and then the size of size t, which is a variable for use after freeze, size of function, which is easy, and then the pool tag, and the type is ulong given in here. We will see what this is in the IDA in a bit. Again, some error handling if use after free variable doesn't exist. it is not going to be able to allocate the pull chunk, and it's going to print it out for us here, return the status. Otherwise, if this variable exists, it's just going to print us a bunch of things. This is really useful, thanks to Author again, when we are exploiting the vulnerability and checking the results in Windows debugger. So yeah, these are going to be useful later. Anyway, what else does it do? Let's go back to OneNote. So we are filling the buffer with ASCII A. You are seeing 41 here, text for ASCII A character. Let me go down here as well. This is the use, sorry, here we go. So for this one, we're using the function RTL fill memory. Let's see the Windows API called documentation, RTL fill memory gets void destination where we are filling the memory with size length for the character that we're putting in, and then what we are filling it with. So again, pvoid, pointer to the void, the type, and then we are putting use after free variable to a buffer. And again, this is the exact same thing, just the size of it to check the length, and we are filling it with a characters. Then what we are doing, we are null terminating the char buffer. So as you can see, use after free into buffer, and you are defining the place that you will put the null, which is calculated with this, the with -1, showing that this is the before the end. Easy. What else? We're terminating with the null character, and then this is also important because we're going to see the continuation of this in the next function. We are assigning the address of use after free to a global variable in here, which we will use later in the next function. We're printing few statements in here, nothing important. We are returning status. After that, the next function is use UFA object. Here we see UFA stands for use after free, obviously. Just stating. So what does this function do? Again, we're printing a bunch of stuff. If the use after free object exists, which is a global variable that holds the address of use after free object variable, right? So if this pointer exists, it calls the callback in here. Cool. So this is dangerous because using dangling pointer will be the reason why we will be successful in this exploit later. Part of the reason. We'll see why in a bit. So after that, we are using the UFA object. We checked if the global variable, which is the pointer to the use after free object variable, exists, which allowed us to do the callback function, calling the callback function. And then we're going to the next function, which is free UFA object, use after free object. Again, we're printing a bunch of things, bunch of statements, and then this is where the vulnerability occurs. If we're going through the secure way, first of all, we're using xFree pull with tag function API call for both of the secure and the vulnerable version. Let's see what is this. We are just calling the pointer. Obviously, this is here the G use after free object, which is the pointer to the use after free object variable, and then ulong tag. If you remember, the tag was pull tag that we use in the first function for the first line, use after free. Here we go. That was a third variable. Okay, so let's see what's going on. I'm going back to my notes. If in the secure version, okay, we are calling this. We are basically, just give me a second. So the xFree pull with tag routine deallocates a block of pull memory allocated with specified tag. Exactly. As you can see, this is free UFA object, meaningful. We are freeing or deallocating a block of pull memory with using this function. After doing this, what we're supposed to do is we're calling this function, and then we are nulling or like putting null for this pointer. In the vulnerable version, however, after we call this xFree pull with tag function to deallocate the memory, we are not nulling this variable, which was the pointer to use after free object variable, which is the reason why the vulnerability occurs. First of all, we are using a callback function, and then we are not nulling it. So this is the whole reason why this vulnerability exists. After doing this, there is another function here, allocate fake fake object, and we're going to use xallocate pull with tag. If you remember, that was the function that we used, xFree pull with tag, that was deallocating, and with this one, if you remember, we also used this before, xallocate pull with tag. We're gonna create a fake object and allocate it in the pull chunk with this function here, and the fourth one, allocate fake object. So I think we have more idea about what did I just say in the beginning of this video with use after free. What are we doing? We'll exploit a stale pointer. What is the stale pointer here? Where was it? Here we go. G use after free object. That is not freed. Here we go. The vulnerable version that is not freed, not nulled. Which is called through a callback function. Or was it? Which is called through a callback function to execute our shellcode after we put it into memory with allocate fake object. I think it is very much understandable right now. It's not that hard at the moment. We understood what it is, what is this, how do we find it, etc. As always, the second item in our strategy is finding the IOCTL. First of all, I will show it in a very simple way. Let me show it like this. As you can see, there are 4 functions, and if you go through the header file, we will also see that there are 4 functions and 4 different IOCTL code. If you go to the common header, you will also see all the IOCTL codes for all of the functions, all of the calls in HEVD vulnerable driver. And if you see every single function that we talked about, allocate UFA object, use UFA object, free UFA object, and allocate fake object, have their own IOCTL code. So there's a very simple way to actually find these. As you can see, there are symbol values in every single one of them. If you write the following in the Python code, this will give you this one, the IOCTL code for every single one of them. I also wrote it down in here, so these are staying the same. You will just change this value in here. For instance, if I write it for 802, which refers to the first function, allocate UFA object, it will give me the IOCTL code. Oh, sorry, here. 804 here as this. Then 805, the next one is this for use UFA object, and correspondingly the others as well. So just a very simple way to do it. Otherwise, you can still also go to IDA. I turned it on in here. This is on right now, but the very simple way to define it is going to functions, IRP device IOCTL handler. This is showing for every single IOCTL handler call. We will go through the first one. Let's see, I think allocate UFA where object is this one. And then if you continue, allocate fake object, free where object, these are all here. What you can do is you can check the function that's responsible for this. You can double click or you can follow through the arrows. As you can see, it's in here. So there's this value here that's an EAX, and for this function, okay, which responsible for this guy, use UFA object IOCTL handler. Oh goodness, let's go back here. Sorry guys. Here we go. This should be 17. H, ignore it. It comes with the IDA. Here we go, 17. And if you look at this one, which is supposed to be this function, free var object, it's supposed to be 4 more because we're subtracting it and we're going back. So 4 more, if you add 7 to 4, it will be B in hex. And the same one corresponding to this one, if you add 4 to B, it will be H. So this is the corresponding one, and the same way you're calculating this one too. But I think this is a much easier way to do it. You just need to check the common.h file, and in this way you can find the IOCTL code without going through IDA, but why not? This is part of the process. Just giving a second way to do this. I'm turning this off as we do not need this at the moment. All right, so let's see what am I doing in here now. I created this very small proof of concept script here. There's nothing different. We're just loading the same kernel 32 DLL as we're going to use it for create file A and device IO control functions. As you remember, we already find these IOCTL codes, and I'm going to try them all in one place, and I will put some breakpoints on the IOCTL handler functions as well. I'm just sending A characters in here to see if IOCTLs are working. This is the only one to allocate the faked object. So I'm putting my buffer here. For the others, I'm just putting none because I'm just seeing if the IOCTL is working. So that's the code that I'm having in here. I'm gonna run it now. So if I go back to here, as you can see, we are already loaded this. If I go to lmnh, have this already loaded in here. If you look at the functions, you can see all of the functions in here. I already put some breakpoints. You can check it with DL as the shortcut. As you can see, I just put it in here. You can just do it very quickly with BP, and then you write in HEVD, exclamation point. For instance, if you use and click on tab, it shows use UFA object IOCTL handler. If you click on tab again, it shows another function that starts use UFA. I'm just putting it on the IOCTL handler to see that if it's working. I'm just gonna start the debugger by saying G. Debugger is running at the moment, and I'm just gonna run this function that I just showed you guys. And as you can see, let me make it a bit bigger, that we just hit the breakpoint, and it also shows on the right side that as breakpoint 2 is hit, which is have to allocate UFA object IOCTL handler. If you look at which one was this, okay, I'm mixing right now. Allocate UFA object IOCTL handler. Allocate UFA object IOCTL handler. The one that ends with 13, which is the first one that we're supposed to hit. So things are working as far as we know. So allocate UFA object IOCTL handler is already kicked here. If you say continue with G, we will hit the second breakpoint, which is free UFA object IOCTL handler, which is the one that we gave in here, 1B. If you go back here, use if, free UFA. And the next one is supposed to be 1F, which is the allocate fake object. Let's see in here with G, allocate fake object. And the last one should be the use one, use UFA object IOCTL handler. As you can see, we hit our 4 breakpoints. That means we have the right breakpoints in here. Perfect. So since we solved this issue, we can directly jump into the exploitation of this technique. All right, so we figured this out. Let's let this continue. All good. So the next thing I'm going to do is I'm going to create the final exploit. We're going to go through a few more Windows API calls, and then we're going to run the final code to see if it's working. So I will show what kind of structure I'm using in my code. Otherwise, it gets really complicated, especially considering how lengthy these scripts are. So the first thing is we're adding the imports, and the next thing is we're going to add DLLs. These are the DLLs that I'm adding: kernel 32, PS API, and NTDLL. I will show you in a bit when I'm continuing the code while I'm adding these specific DLLs and why these are needed. Which Windows API calls we're using that uses these DLLs. We will see it in a bit. As always, I will do the handle. As always, this is nothing different. If you check my previous codes, this is exactly the same. So that's why I'm expecting you guys to not have any problem with that. We're using create file a Windows API call, and we are using kernel 32 DLL for the specific Windows API call. We will use another function later for calling the IOCTL calls, and again we will be using kernel 32 DLL for that one as well. So that's why we need that one. There is nothing different, and this is the error handling in case handler is not created. Okay, for the shellcode, this will be exactly the same as the previous one as well, so I'm not going to explain anything different. These are already created in the first video in the Stack Overflow, so this shouldn't be a shocker as well. Just put it in the shellcode area from the previous video. Again, defeating dep with virtual alloc, this will be not a shocker as well. The same thing that we used in the last 4 videos as well. Nothing different, the same thing we're going to use to allocate the memory first, and we'll write the explanation as well. So we're going to create the RWX memory. We will copy our shellcode in that region. And this is the way to defeat dep so that we can bypass it. Again, call the shell. This is nothing different. The same thing that I'm using in the previous videos over and over again to start a new CMD shell here. So after that, there are the different parts coming. We're going to define a buffer here for spraying, creating the holes, um, spraying the objects. We're going to create a buffer here. So there will be one line code in here. We're going to spray the object. It's just a for loop. It's a very simple code. You will see in a bit. Then we will create the holes using another Windows API call. And then very simple, we will call the IOCTL code in the correct order. Before doing that, let me create these few objectives as well, because this will have a complementary allocate fake object line that will explain everything. So let's start with the spraying part, which is specific to this exploit. We will write a one line of code to basically create the buffer for the spraying the object. So we're going to create this variable spray event and define it as a buffer. And then in here, we will spray the objects with the following Windows API call. So these are the line of code that I mentioned in the beginning. There's just a for loop. There's, as you can see, 10,000 objects that we are spraying. And using this variable that we created spray event, and we're going to append it to the buffer. And then we're going to use ntdll DLL that we defined in here. That's why we use this one. So we're using this function ntallocate reserve object to first spray 10,000 and then 5,000 objects. Right after that, we will create holes. And then we're creating holes in this sprayed region using close handle. Again, it's using kernel turtle to DLL. It's pretty simple. With the for loop, we're just creating a hole on these sprayed regions. And then we're going to use the IOCTL code in the correct order. And this is the last line of code that we're going to use to call IOCTL code in the correct order. As I mentioned, this is very logical. We need to first allocate UFA object and then free it, and then allocate our fake object here, which is going to be shellcode, plus our junk, which is ace characters. And then we're going to use the UFA object. The IOCTL code is in the same order as we use in here when we were debugging it in the first place, if IOCTL codes are working. So this is completely the same. The only difference is here, we're adding the fake object. The point address here is the variable that we use when we're defeating that with virtual alloc, which takes the shellcode. So this is the code that we used in the previous videos as well. We're just adding it to our fake object in addition to our junk at the end, and we're just spraying it for the range for the hole that we created in here. If you remember, spraying event for 5,000, we use it here to create holes, and now we are just allocating our fake object into these created holes to spray the object. So let's see how it will work. When we run the exploit, we just get a shell, and when I ask for who am I, it gives the NT authority system. So I don't think it's so complex comparing to a few of the exploits for HEVD. It's lengthy, but most of the things are the things that we are using from the previous exploits. We know the format now, how to use these, how to create a handle, how to create these lines for device IO control in the code. We're called IOCTL code. Yes, there are 4 functions here for 4 different IOCTL code, but it's logical. We understand the code, we understand the source code. So we have an idea how to actually use this order, first allocating the object, freeing the object, allocating our fake object in it, and using the object. And it's pretty simple when you understand the logic. Of course, these are like new methods. If you're especially seeing this for the first time, it's kind of shocker, but it gets normal in time when you use it in different cases. So if we need to summarize it, what we used in here, these are all the things that we used from before. The only different thing that we use for this technique is first we're spraying the objects in here, then we're creating the holes, and then we are using the IOCTL code in the right order. And when it comes to allocate fake object, we are using our fake object for the point address variable that we defined in here that uses shellcode, plus some junk that we send to see if we are allocating in the memory. And then we are sending it or spraying it into the holes that we created same length that we defined in here for the whole as well. It's spray event2 variable. And then we are popping the shell. Hope this is clear to you guys. Hope this is helpful in your journey when you're learning kernel exploitation. I'm still in the process. I'm also doing a bit of browser exploitation research lately, but yeah, I'm trying to just make it as perfect as possible while I'm in my learning process. Hope you like it, guys. Drop a comment and see you in the next video. Cheers, guys.